Now we're going to cover the SPPF module in this section. So again, as we've done before, we're going to work with both our Colab environment as well as VS Code. So the first thing I'm going to do is open our Colab notebook. And in particular, I'm going to go all the way here to the bottom, SPPF module. If you're coming from the previous videos where we covered the C3 module, you will not have to do this step. But if you're jumping into this video, you will have to. So what we're going to do first is go here, the texture model, and just click and then run cells in section. This will load our model. And then we'll connect to Google Drive to access our files here. And now we can close this and maximize. The SPPF module or layer stands for Spatial Pyramid Pooling Fast. And the one used in YOLOv5 is a specialized variant of the Spatial Pyramid Pooling layer. The original SPP comes from this paper. And in Glenn Jocker's words, the SPP in YOLOv5 is different from the one used in the original paper. In particular, the SPP does not include fixed size vectors, but instead they have a fixed number of channels with the spatial dimensions that depend on the input image. And we'll cover this in much more detail. The purpose of the SPP layer is to aggregate context at different scales and enhance the receptive field, which is beneficial for detecting objects in various sizes. Now, the SPPF layer is an optimized version of the SPP that uses fewer resources while maintaining the benefits of multiscale feature aggregation. So as you can see here, it applies a max pooling operation multiple times in sequence, first max pooling, second max pooling, and third max pooling. And each time, the result of the previous pooling operation will be the input to the following operation, creating a pyramid pooling effect. You can also see here the differences between SPP and SPPF. The SPP architecture, after the convolution, Button, and Silo activation, applies 3 different max poolings, each of those with a different kernel size. So 5x5, 9x9, and 13x13 kernel size. And all of those 4 get concatenated. And then you have an additional conf class here. In contrast, the SPPF module applies the same max pooling with a kernel of 5x5 3 times. And the output of each of these max poolings has the same dimensions, as we'll see in just a moment, because we're applying a padding of 2 on top of the 5x5 kernel. And then we concatenate the 4 outputs, the one from the conf class, as well as each of the max poolings on the channel dimension, and then we process it with an additional conf class to obtain the final result. Now, it's important to mention that this is one of the changes compared to its predecessors that YOLOv5 has incorporated. And in fact, the original releases of YOLOv5 actually used the SPP module, and then later on, it was migrated to SPPF. And you can see it here. If we go to tags, and then YOLOv5 release 6, if we go to the commit, if we scroll down, and in particular, we select, for example, the architecture that we're using, YOLOv5L.YAML, you can see that from YOLOv5 release 5 to YOLOv5 release 6, the SPP layer got changed to an SPPF layer. And in fact, it was also moved after the C3. In YOLOv5 release 5, SPP was before C3. In YOLOv5 release 6, SPPF was introduced to the architecture. You can also see some of the other changes that were made, such as the number of bottleneck loops that was reduced from 9 to 6 in this C3 module, as well as the initial conf class that was originally a focus class, as you can see here as well, and you can read more about it if you like. So in essence, the advantages of the SPPF module is that it is efficient at capturing multi-scale features that allows to recognize objects of different sizes. It is also much more efficient since we're applying one max pooling layer sequentially, which also simplifies the architecture and helps with memory efficiency. You can also see the speed improvements of the SPPF module, which is more than twice as fast. And that is because in the SPP architecture within YOLOv5, you have 3 different max pooling layers, and each of those get the input and perform that max pooling. And then each of the outputs gets concatenated with the input, with X. As you can see here, the output of these max poolings get concatenated with the input, and then an additional conf gets performed. While with the SPPF architecture, you have one single max pooling of 5 by 5, and the output of each max pooling is the input to the following max pooling sequentially. And then you concatenate the input X with the output of each of the max pooling layers, with an execution time that is improved by more than half. Now we can also explore this a little bit more. So if I load the input image and I go all the way to M9, meaning stage 9, which is the SPPF module, as you can see here, SPPF, stage 9. Then if I run this, you can see that we have an architecture of 2 conf classes and 1 max pooling. If we go into M, you can see we have the 2 conf classes and the max pooling. But we can also visualize it even better. So let me step over this and I step into the SPPF class, which is right here, common, SPPF. So when I run that, will be right here. And you can see that self has 2 conf classes, CV1, CV2, and then 1 max pooling that gets repeated 3 times. As you can see here, we have X, which is the input, but also the output of this conf1. Basically, X is this, but also gets overwritten. And the new X is this value right here, right before going into the max pooling. And then that X gets max pool. So Y1 is right here, as well as right here. Y1 is the input to the second max pooling to get Y2, which is this output, as well as this output. And then we get an additional, which is this one. And we concatenate the input X coming out of the conf1 class, conf1, the input X, Y1, Y2, and then this third max pooling, X, Y1, Y2. We could have called this Y3, but there is no need to store that variable. So we're just feeding it directly into the torch.cat to concatenate it in the channel dimension, dimension 1. And then all of that gets fed into the conf2 that is defined right here, which is this one right here. And then the output will be the input to the next stage. Now we can also call M9.m to obtain the max pooling arguments. And you can see that the input is kernel size, stride, padding, dilation, etc. As you can see here in the documentation as well. So the output that we obtain here, X out 9, meaning this value right here, we're going to do it step by step and see if we obtain the same result. So we have the output of stage 8, and then if we feed that to the convolution, then we obtain this output. And then sequentially, we'll feed that into the first max pooling layer, obtain this value, and then sequentially to the next one, and obtain this value, and then sequentially to the next one, and then obtain this value. We will then concatenate those along the channel dimension, and then we'll apply this second convolution to obtain this output. So let me run that, and we obtain this. And there is a few interesting things to observe here. The first one is that the input to this SPPF module has the shape of 1 by 1024 by 20 by 20, as you can see here. And then the first convolution is going to be shrinked by half. So the output right here has these dimensions, 1 by 512 by 20 by 20. And then what's very interesting is that the shapes remain the same through these max pooling layers. So the 1 by 512 by 20 by 20 gets maintained. And the reason why that is possible, I did mention it briefly earlier, is because we have, as we said, a 5 by 5 kernel, but we're applying a padding of 2. So by applying a padding of 2 to the output with a kernel of 5 by 5, we maintain that same shape size across these outputs, which when we concatenate those 4 along the channel dimension or dimension 1, we obtain 1 by 2048 by 20 by 20. And the nice thing about this is that we've done it by aggregating features that are at different scales, because the scale for this one is different from this one and different from that one, because each of those are applying a max pooling. And then that output gets convoluted to obtain the final 1 by 1024 by 20 by 20, which, as you can see here, is the output of the SPPF module.